Hello everyone, my name is Fiona Leitner and this is my AP Calculus project, The Broken Railroad. As you can see, here is my rational function, r of x, and here is its graph on the right. So my function is modeling a railroad. As you can see here, it matches up, and later into the slides I will explain why there are breaks in the railroad and water as a river blocking the railroad. And my character that I'll be using for this is Daisy from Animal Crossing. As you can see here, she's going to be the one going across the railroad. So first we have the function conditions. As you can see, it is a rational function because it takes the form of f of x divided by g of x. Next you can see the roots of f of x, 0, 1, and 3, and the roots of g of x, 1, 3, and 2. For my third criteria, you can simplify the function so it becomes x over x minus 2, and then the 0 would be at 0. Since when you plug in 0, you get 0. That's the root. Next, again, by crossing them out and finding the simplified version, we can find the vertical asymptote because r of x does not exist where x equals 2 because you cannot divide by 0. The function will not exist there. Next, we have the horizontal asymptote. Since the leading coefficients are 1 on both the top and the bottom, we divide them and that gets us 1. And we can do this since the degrees of the top and the bottom are the same. So the horizontal asymptote is 1. Finally, we can see that there are two holes, one at x equals 3 as it is crossed out. It's a factor crossed out on the top and bottom, and one at x equals 1, which is another factor crossed out. And these are removable discontinuities. Here is a 10 by 8 scale or a 20 by 16 scale of the graph, and we can see the holes and the x-intercept. Here we see the vertical asymptote at x equals 2. Hopefully now it makes a little more sense why there is a stream blocking the railroad. Those are the infinite discontinuities or the asymptotes, and the removable discontinuities are the holes in the railroad, as you can see. And so here's the end behavior. As x goes to infinity or negative infinity, r of x approaches 1 because of the horizontal asymptote at y equals 1. Then we have the removable discontinuities at 3, 3, and 1, negative 1. Those are the holes, and the vertical asymptote. So as x approaches 2 from the left, r of x goes to negative infinity, and as x approaches 2 from the right, r of x goes to positive infinity. Here we have the derivatives. So for the first derivative, I will be using the quotient rule, and as you can see, I get negative 2 over x minus 2 squared. For the second derivative, I changed the form slightly, so then I can use product rule and chain rule, and then I get 4 over x minus 2 to the third. Here's the graph one more time for reference. And now we can go into graph details using the derivatives. So the first derivative will always be negative, since a negative divided by a positive will always be negative. And it does not exist at x equals 2. There are no critical points since it's always decreasing. It never changes from decreasing to increasing, and so there are also no maxima or minima. For the second derivative, if x is less than 2, the graph is concave down since it's negative, and when x is greater than 2, the graph is concave up since it's positive. Here is my mean value theorem problem. So we have from the interval from 0 to 0.5, and a railroad inspector is analyzing the direction of the damaged track. We have to find somewhere between 0 and 0.5 where the instantaneous direction change will match the average direction change. That will be the value c. So first, we're going to find the average value, and so we get it's negative 2/3 by plugging everything in. And then we're going to plug that in to the derivative. We're going to set that equal, and we're going to find the value c, where the derivative is equal to the average. And as you can see, there's two values, but only one will work on this interval. Because 3.732 is out of the interval, it has to be 0.268. Next, we have the intermediate value theorem. So as we can see, there has to be a 0 in between these two values, since 1/3 and negative 1/3. 1/3 is greater than 0 and negative 1/3 is less than 0, so there has to be a point in between where it's exactly equal to 0. And when we look at the graph on the right, we can see that that is true. Next, we have the extreme value theorem. So in this interval, there has to be a maximum since it's continuous, and a minimum, a relative minimum and a relative maximum. And as you can see, this is again true. At -4, there is a maximum at 2/3, and at 0.5, there is a maximum at 1/3. And we can see this is true by looking at the graph on the right. Next, we have the tangent and secant. We have to use the derivative, and we will set x to 0 in the derivative to find the slope of the tangent line. That's what the derivative is. So we get y equals -1/2, and then the opposite reciprocal will be the slope of the normal line. And that, I have it in point slope form there, but in normal form, it would be y equals 2x. And as we can see on the graph on the right, that is the tangent line and the normal line. Thank you.